That's what I was asking. I was like, that's what I said.
All right, I think we're about ready to get started. Thank you everyone for coming. I'm so excited to share this with you. We are presenting Manna. Ta-da! And let's go ahead and get started. This is our Barrett Honors Thesis.
One thing for the people on Zoom, because I know our entire committee is on Zoom, as of now, we don't have speakers to hear anybody that talks on Zoom. So if you guys can put something in the chat, Noah's keeping an eye on the chat and let us know when it's come in. And hopefully classroom support shows up in the next couple of minutes and can help us get those speakers working.
My name is Audrey Schlichting. I'm a fourth-year engineering student and a flight student. And
My name is Lukas Severinghaus. I am a third-year robotics engineering student with a secondary focus in unmanned aerial systems. So what we're going to show you here is a video from the UN World Food Project. So they're one of the largest humanitarian aid organizations in the world. And when they can't get a truck or a boat in to deliver food in an area, this is how they do it.
When Oscar 050 Hotel, you're clear to drop.
Each of those bags is a 50-pound bag of soybeans. They bag them 7 times, bags inside bags, because they just throw them out of the back of an airplane, and they're going to break 6 bags by the time they hit the ground. But the 7th will still continue. This is one of the best equipped humanitarian organizations in the world, yet they don't have a better method to deliver something than just throwing it out of the back of an airplane.
so the main problem is that it's really unsafe. So all of the people underneath the drop zone are in danger of being hit by the food that is being dropped above them. It's also unsafe for the pilots. They have to fly at a really low altitude in order to do these drops precisely in a specific area. And typically it's inaccurate because they have to do it over a very specific area. And as you saw, the drop with all of those was very scattered. Again, very difficult to do this. And potentially for the pilots, if they're flying into unflat terrain, they could fly potentially really close into mountains. So a solution that is required is something that's automated, it's helpful for the pilots and the people below, something that's lower cost, and something that is steerable. And we'll talk about why Manna provides all of these in the rest of our presentation.
So just a little bit of background on our project itself. We're students in Barrett, the Honors College here at ASU, and the thesis is part of the Barrett experience that we take through our 4 years here. And it provides us an opportunity to look into an area of interest and to explore it a bit further within the realm of a quasi-academic endeavor. So exploring a project is really of interest to us. We chose this project because of mutual interest in missions aviation and how we can apply engineering and aviation in a humanitarian space like this to resolve some of these problems. This project is now 13 months old. We started in February of last year, and this is kind of a landmark for us as far as finishing the total project, but it'll be continuing on. As a kind of fun fact, the name Manna itself comes from the Bible, where God provided food from heaven to the Israelites who were wandering in the desert. So in that sense, it was one of the first aerial drops of food in the world. So our project's assisted by a committee of 3 faculty. All of them are on Zoom today. Professor Anthony Wende is with the aviation department inside the Polytechnic School. Dr. Deana Delp is here with this Polytechnic School as well. And Dr. Timothy Takahashi is from the School for Engineering of Matter, Transport and Energy. So over the next about 40 minutes or so, we're going to be covering kind of an overview of missions aviation groups, who they are, what they do, and then the solution that we built and how it can apply against some of those problems they're experiencing.
So mission aviation group. So we saw a video about one example of that, but who are they and what do they do? So mission aviation groups typically deliver relief and medical supplies, food, equipment to places with limited infrastructure. So you see a couple of examples here in the top right. They're delivering passengers for medical purposes, and the bottom left delivering cargo and people for transporting to a different location. So we interviewed a couple different mission aviation organizations, including MOF and JARS. And so a little bit about these two. MOF has a fleet of about 41 aircraft over several different locations, and they transport approximately 4.3 million pounds of cargo per year. And that's a lot of cargo. And with the aerial drops being so dangerous, it is fantastic if we can make it better. And JARS, General Aviation and Radio Service, they are more of an R&D research and development company, so they're hoping to make the aviation space a little bit better. And so we have a picture of the different kinds of aircraft down at the bottom. So the one that we just saw in this in the video was really large aircraft carrier, and now we see this is typically for mission aviation groups. They typically have a smaller 4 to 6 seater aircraft, and these are just a couple of examples of the things that they have. So the main problem, we're kind of recapping from earlier, super hazardous to do these drops. Imagine you're flying a plane. So you're flying, pitching up back and forth with one hand. You're doing your power settings on the other hand, but then you also need a third hand to grab the cargo and dump it out of the window. That's really scary and hazardous to do for one pilot. And so typically it's better to have an aircraft that is able to do these cargo drops. So they would have to modify the aircraft to do that, but it's way more expensive for these groups to do that. But they're operating on limited budgets as humanitarian organizations. So they have to make do with what they have, which is a little bit more hazardous.
So we looked at some existing solutions to see what are companies already doing to try to mitigate some of these problems. Zipline is a kind of newer player in the space, and they've been using drones to do deliveries in Rwanda and deliver medical supplies. These drones can carry a payload of 0 to 3 pounds, and you can go about 95 miles an hour within a 50-mile range. So it's really effective for short-range operations, but the issue is that they require a lot of United States infrastructure to operate, and they need a lot of integration into the national air, the air infrastructure, because these have to operate alongside the air. Additionally, another solution we looked at, and one we kind of based our project off of, was the JPAD system, the Joint Portable Air Delivery System. This system is developed by the military to deliver cargo where they can't drive a truck in, or it's too dangerous to be in a convoy. So they can take anywhere from a 10,000 or 10 pound to 42,000 pound payload. So they can drop a full-on vehicle out of action. But the problem with this is that it's extremely expensive, anywhere from $30,000 to $600,000 per unit. And it's also covered under the ITAR, which is the International Traffic in Arms Regulations. And basically, it's classified as military defense equipment, and it can't be exported outside the US. So that restricts usage, especially in organizations that are operating in areas outside the US, and organizations have a limited budget because they can't be paying $30,000 per unit. We're running the classroom audio through this one, so we weren't able to get the speakers to work.
Okay.
Yeah. So the need really is to develop a low-cost system, something when we talk to organizations, they want something that's under $200 a unit, something that can be deployed from one of these small aircraft, not from a really big cargo airplane. With this, they really only need to have a small payload. most of the times, if they're doing drops, because it's so dangerous, they're doing it in life or death situations. So delivering a small amount of medical supplies, food, or emergency relief. It needs to be safe for them to operate. It needs to be an easy load on the pilot. It can't require a lot of their resources in flight to coordinate when to release it. It also needs to be able to operate in areas that don't have a lot of infrastructure, where there might not be existing roads, networking, think about like cell service, things like that, and also operate in areas that are not under ITAR control. So it needs to be civilian grade, basically, so you can be exported to various places. One of the applications we've looked at is using it in Syria, where they just had an earthquake. Syria is one of these places where you can't export a lot of technology because it's a conflict zone. So having something that's not classified as military equipment makes it a lot easier to get clearance to move that equipment into that area to help those people. So what is Manna? What is this device we built? So Manna is 3 different components here. So we have a parafoil. This is a custom wing that basically lets the vehicle glide down as it's flying. We have the hardware, which is the flight vehicle here, and it composes a couple different parts that we're going to look at here in a minute. And then the software that runs on that lets it navigate down to the ground. So why use a paraglider? A lot of people right now are talking about how we can use drones or drone delivery, things like that. The biggest reason for a paraglider is that it's simple. There's really few moving parts. There's no propellers that can injure anybody. It doesn't require a lot of power to operate. Like existing skydivers, it's really easy to deploy one of these from the airplane because wing can inflate in the air, and it also can't fly away. A big concern is that you don't want a package that you drop that gets confused and flies 50 miles away. Because this is falling, it can't actually climb, it can't go farther outside of its drop zone. And from a government perspective, it's a lot safer option because once it's dropped, it will be on the ground in a matter of 60 seconds. So there's very low risk of it interfering with other aircraft in the area.
So a little bit about the parafoil. As you see here, it's a very large display in front of you. So a little bit about the parafoil design. This is a ram air parafoil design, double skin. That just means that there's 2 layers of fabric here, and as the air goes through, it inflates the fabric and makes it sturdier. So this is really helpful in creating a greater structure for the aircraft, since it's not made of metal or something harder and sturdier. It is affected more by wind. So having it a double skin and inflate gives it greater stability. So this is really similar to a paragliding parachute. As you see in the front here, we have these green lines in the back, and it attaches to servos that allow it to move right and left. And so that gives it greater stability to be able to move right and left. And the NACA 4412 is a specific shape and design of the airfoil. So it has greater low speed handling characteristics. So when we're thinking about the airfoil design, we at higher speeds, you want the thickness of the airfoil to be a lot thinner so it can glide through. And at slower speeds, you want it to be a little bit thicker. But we also want a good balance for stability with this airfoil. So that's why we chose something in between. It's the NACA 4412. And so at the bottom, you'll see that surf plan image on the far right. So this allowed us to get the NACA 4412 airfoil, put it into a 3D model, and then we were able to go into the innovation hub, just the lab right across the way over there, and we were able to get the 3D model onto 2D paper and get the laser cutter to laser cut all of the fabric that we used for all of this. So it was many, many hours of fabrication and sewing, putting it all together, and now we have this, and it is fantastic. And we'll talk more about how it tested in just a moment. And a little bit about the hardware as well. So we see this guidance system at the bottom. So in this gray box that we have in the center, that contains all of the electrical components for this. So I don't know if you can see my mouse. Yeah, you can. Just a little bit. All right. So this gray box right here houses all of the electrical components for this, and it's attached to the parachute via the 2 servo motors on the right and left hand side, and that is what interfaces with the payload here. So we have the aluminum pieces, and the payload is attached beneath that.
So the electrical system on board is really split across 3 components. We have a computer on board that performs all the navigation computations. that is similar to a Raspberry Pi. So it's just a really low cost computer. It costs about $15 for us to purchase. There is a co-processor system on board. The problem with the computer is that it can crash, or it can take really long to start up, or it will freeze, just like your computer at home. So the coprocessor is a really lightweight, fast mini computer that can connect to the sensors and perform some very basic functions, but then coordinates with the flight computer for more complex operations. And then our power system is combined of the battery. There's 3 different power regulators on board for redundancy and safety across the systems. And then we also have our servo motors that pull those cords that let us turn. All of these parts are kind of connected in this block diagram. And it's pretty simple, working from right to left. We have the battery on the far right side. The battery provides power to the 3 different orange power supplies. The flight computer connects directly to the coprocessor, and the coprocessor connects to those sensors. So basically, we can swap out the flight computer with a different computer and maintain the coprocessor with all of those sensors without anything changing, because there's some really simple interfaces. It's like a drop-in, drop-out system where we can swap pieces really easily.
Right, a little bit about the hardware frame. So I love Legos. I'm sure many people in here love Legos. So we have the engineering equivalent, engineering Legos is what I like to call them. It's a Tetrix kit. So the aluminum bit that you see on the side here, right here and here, that's from a Tetrix kit. And that was just allowed us to have easy manufacturing of the structure for it. And we have an acrylic laser cut skid plate, which is not there. We'll talk about that in a little bit. And we also have some internal parts that were layered with some acrylic to give some spacing. And we have, again, the gray box, and some of the design features include a low center of gravity. So we want it to be a little bit lower, so it has more stability. And the servos to be spaced out enough to, again, provide that stability, because if they're too close, it's like being on a bike. So we want to have it similar to being on a car, a little bit more spaced out. And yeah.
So the software is really what enables the vehicle to do anything. By itself, the hardware can't go anywhere. But in order for the vehicle to fly, it needs to do 4 key things. It needs to be able to plan a flight, then know where it is in the world. And then based off of those 2 things, it can determine how it needs to navigate to get to the final drop zone. And at the end of the day, we need to do all of this in a safe manner so that nobody gets hurt and that we don't damage the payload or the vehicle itself. Additionally, for development, we also wanted to be able to remote control the vehicle in case the autopilot malfunctions, to be able to log all the data from the sensors so we can analyze it and see what do we need to change, and then also be able to review and analyze that data on the ground after we have completed the flight. So the flight computer runs all the navigation and control algorithms. These are built out of the Python programming language running on top of MQTT. MQTT is a message bus, and it basically lets a bunch of small programs talk to each other and share a task. So instead of writing one really big program that does everything, we have a bunch of really small programs that all work together to do each of the aspects of flight. And this makes it really easy to develop them because each one has a very small task that it can work well at. And when there's an issue, we know which section to go in and try to debug. The coprocessor runs a similar code, but it runs at a lot lighter weight. And it does that because it needs to run a fail-safe mechanism. So it checks to make sure that the flight computer is operating safely. And it also interfaces with the sensors that are on board. The flight control, if I can geek out here for a minute, uses an architecture called successive loop closure. And basically what that means is that we have, like the layers of an onion, successive layers of control. So at the very outer layer, we take a flight plan into the vehicle. The flight plan and the global path planner determine what is the next waypoint the vehicle needs to go to. So that's the outer layer. That waypoint needs to travel to is passed to the next layer in. That is the local path planner. The local path planner takes the waypoint and determines which way do I need to turn in order to head to that waypoint. And then the final layer on the inside is the heading controller. And based off of knowing which direction it needs to go, it determines the actual commands to send to the actuators to turn the vehicle. So together, each one of these builds on the capabilities of the inner systems and provides a lot more complexity at the very top level, breaking it apart into several small pieces. Additionally, we looked at doing wind estimation. One of the things about a parachute is it's very light. It's very easily influenced by wind. This thing can be blown off course, downwind, and you can prevent that from landing at the drop zone. So we've looked at a lot of ways about how we can determine where the wind is, and when we're in flight, automatically adjust the flight plan so that we don't fly, for example, downwind where we wouldn't be able to land later, or we'd have to crash land somewhere else. The coprocessor runs a much simpler program, and all it really does is it checks for three things. It checks that the flight computer is giving it a heartbeat. So about twice per second, the flight computer checks in with the coprocessor and says, I'm alive, I'm functioning. If that ever stops coming, the coprocessor knows that the flight computer has failed and will take over control. Additionally, we had a controller on the ground, the human pilot. So if the vehicle went awry, we could take over control. It checks to see if that controller is connected and if the pilot on that controller has flipped a switch saying the system can be armed. Until the system is armed, none of the motors can move. And that means that as the vehicle is being lifted up or once it hits the ground, we can prevent the motors from moving and potentially damaging them if they jam into the ground or if they tangle in flight. So really, this just helps prevent the vehicle from flying away or damaging the servo motors that are on there. Off board, we collect all the data from the flight and then we download it into a visualization dashboard. And this lets us have really good time-based views about where the vehicle was and what all the sensors were doing at a particular moment in time. And this lets us really easily correlate different sensor values. Like for example, looking at how our altitude matches with our acceleration. Because when we see a really large acceleration, we probably know we hit the ground. And at that point, our altitude is the altitude that we were at the ground. So it lets us see those things and play back that data in real time after the flight to analyze were things successful and what can we change.
Moving on to testing. How did we test this big contraption? So there are a couple of different ways that we tested it. First, we did simulation testing even before we created all of this to see, okay, can we develop a flight plan? Can we develop a guidance system? How is that going to work? And yes, it did. We'll talk about that in the next slide. Parafoil testing. We were able to do a couple different kinds of drop testing and field testing for this to make sure it inflated properly. And full vehicle testing, we took this, used that big drone that's in front of us here, and we're able to lift it. And we'll explain that a little bit more in the third slide.
Yeah, so our first step was doing simulation testing. The idea is we don't want to write code and then put it up in the sky and see if it works. We want to be able to test it before we fly it, so we have the best chance that the vehicle will actually work in the sky. The problem with testing in person is that they have about a 20-second flight time. So that means there's 20 seconds for us to test a change before we have to re-prep the vehicle, pack up the parachute, get it ready to take off again, about a 10-minute process. So we did a lot of testing called software in the loop testing. Basically, we run the real flight code, but we run it on a fake vehicle. And that vehicle runs in a simulation. And that lets us change things like the weather, how big the vehicle is, or how much weight is on it, or what algorithm it's running, and lets us see the data that's getting the output and tune that so the system works as well as possible before we deploy it out into the real world.
Here's a short video of some of the testing that we did in simulation testing. So in the bottom left-hand corner, you'll see that aerial view of what's going on board, and on the top right-hand corner, you'll see that position map of approximately where it's going over the ground. This is played at about 60 times speed, so it's going to be a lot faster than it actually is. In a moment here, it's turning, and then you'll see it spiral down as it's coming around its target area.
The spiraling is really important for us because it lets the vehicle stay in the area where it should be, but still get rid of altitude. So basically, we just keep going in circles, and that way we don't make a really long path somewhere else and get away from where we should be.
I believe that airport we tested it at in simulation is Sky Harbor, so it's around the area. For the parafoil testing, we tested this at Desert Sky Park, which is about a 3-minute drive over there. And for this test, after we manufactured the parafoil, we were just trying to test, can this thing inflate properly? And so we took a powered paraglider unit at the bottom, and we were powering it on, making sure it would work. And we realized we actually designed this for falling and drop testing. So that test proved that it inflated properly, but that it wouldn't climb, which is anticipated. So we did more drop testing at Santan Hall, which is the building right next door. And we dropped this from the 3rd story, and we just made sure that it would, again, glide and flare properly. And that was what we found.
Yeah, so we did about 15 drop tests from the building, but we realized, again, we only get about a 4-second flight time, which is not very much for us to be able to test anything. So we figured we have to go higher. But the problem is, there's no buildings around here that are any taller than these buildings here on the 3rd floor. So we ended up working with the aviation department to purchase this drone. This is an Aurelia Aerospace X6 standard. It's a 6-propeller hexacopter that has a payload of up to 11 pounds. So it's able to carry up our vehicle and has an endurance of 35 minutes. We can conduct multiple tests on one set of batteries and carry the vehicle up to 400 feet. That 400-foot limit is actually because of the FAA. Because it's classified as a drone, the entire system can't go higher than 400 feet. But in additional testing, we may be able to get permission later on to take it to higher altitudes and test it for a longer flight time. So we did 2 sets of testing with the full system in the vehicle. Unfortunately, the drone took us about 3 months in order to get it purchased. So that delayed our testing, so that we were only able to do 2 test flights, or we had to wrap everything up as this project was completed. We did our first set of tests in a local park in the beginning of February, and then with that one, we were just testing that the drone was functional to make sure we didn't get a broken drone out of the box, and dropping just the parachute with a fixed weight. And that just lets us see, does the parachute even fly before we drop all of our fancy electronics and hardware on it. And then we did a second, more complete set of testing with the full flight vehicle, and where we recorded sensor data and we were able to steer it and see how does it perform.
Here's a quick video of the 3rd test that we took at the park just right across the street. And this was a very successful test. So you'll see a little explanation of what's going on. The drone is lifting up our vehicle. And as it gets to, I believe this test was approximately 200 feet. As it gets to 200 feet, you'll see it release and you'll see the parachute descend down to the ground. So this was approximately a 3-man crew. So we had Lukas operating the X6. Myself, I was operating the servos for the vehicle. And we had Professor Wende. He was actually operating the drone, which is the drone footage that we're watching now.
To prevent the parachute from tangling into the drone, so we don't want to crash this really big drone. We have a 10-foot cord that runs from the parachute up to the drone. The drone has a little release mechanism. So once we get up to altitude, we just release it and those cords will dangle free as it flies down.
Right, and going into the analysis of that. So we just saw that. What was that? Was it a good test? Was it a bad test? It was a good test. And so some of the things that went really well during this test was the parafoil performing exactly as expected. It was very good. And the detachment from the X6 drone also worked really well. There's a servo underneath the X6. And so once it got out to altitude, then we were able to detach the servo and it was able to come down as we just saw. So those worked really well. A couple of things that we learned from things that didn't go quite so well is the deployment method was absolutely critical. So when we saw it going up, on that test, the strings didn't get tangled and they performed exactly how it was supposed to. On some of the other tests that we saw, as the vehicle was lifting up into the air, the wind was actually so violent that it was tangling all the cords around the flight vehicle. And so that was creating partial inflation, which you can see in the bottom right-hand corner. And so the wing wasn't properly inflating. And so because there were short flight tests, that means that we had to be on our game and making sure that all of our flight reporting data was operating properly as we were going through these tests. And the sensor sampling rates needed to increase. So if you think of like a heartbeat, when we were testing this, it was testing the impact and the acceleration that we were seeing was sometimes on the peak of the heartbeat and sometimes it was not. And we were realizing, okay, well, why is that happening? And it was because it wasn't going fast enough to be able to see exactly when that peak was. So increasing that rate would be really helpful and when we're going on future tests. And task saturation. So there were 3 of us operating all of that, realizing we probably should have had a larger crew. We probably should have had someone cross-checking and making sure that we're going through everything, that all the flight data was being recorded properly. And so looking back, I think that those are some of the things that we definitely learned from the flight tests that we conducted. And so this is an example of one of the tests that didn't look quite so pretty. So this one had partial inflation, as we'll see in just a minute. You can see the strings were getting tangled on the far side of the flight vehicle, making it not inflate as it's supposed to. And you can see the acrylic shield in the front totally broke. And so as we were continuing on our flight tests, we were actually testing the rest of our vehicle without a skid plate, and it was fine. It worked out.
So kind of to wrap things up, where are things at with this project? We have been trying to build a complete system, but in a sense, we reached for the stars. What we really built here is a solid foundation. We have all of the core components of a delivery system like this that need to be in place. These systems are really modular, so it makes us easy to develop one particular thing. For example, we can swap out the parachute, but the entire guidance unit can stay the same. Or we can change the frame, but the software and electronics can stay the same. This will make it really easy for further development to swap out those parts. And as far as the development goes, we have some of these really critical pathways in place. We worked with a manufacturer in China to build the fabric that we needed and to have that supply chain in place to get enough of the fabric in the time span that we needed. The electrical architecture of the design has worked really well for us and can continue to be used on further vehicles. And the way that we design the software makes it easy to test further options without having to redesign the entire system. But perhaps most importantly, as we all do as engineers, we've identified the areas we need to improve and we know what to work on next. So looking back, we were looking back at what the customers needed at the very beginning. They need a system that's automated. And our system provides autonomous navigation for them, basically hands-free. It needed to be a low-cost system. We're going to talk about cost here in just a second, but at quantity, this entire system is less than $200. From a safety standpoint, we have layers of redundancy that make sure that the vehicle will continue to operate safely and keep both the flight crew, payload, and the people on the ground safe. And finally, from an ease of use standpoint, it's fully autonomous. There's no human intervention required to get it to the ground once it's been released. From a cost standpoint, this single vehicle, as you're seeing here, costs $243 in materials. These numbers can go down really quickly when we go to start produce a small production run of even 10 units, because we'll start to buy things in quantity and the prices just come down. One of the things we didn't consider that we'll have to look at more is the parachute assembly time. All in all, we spent about 40 hours of time to design, cut out, and assemble this parachute. There's about 99 unique parts that make up this parachute, of fabric and cord, and every one has to go in a specific spot. So with some optimizations about how we design that, where we can make some of the parts, combine them, or simplify how they are, that can reduce that cost and make it a lot cheaper to produce that at scale.
So some of the lessons that we learned, this is some great practical design experience. We're able to understand a little bit more about aerospace software and hardware design. And so system design and integration as a whole, understanding, okay, where do we place the different cords in the bridle. How do we manufacture? How long does this need to be? How heavy is it? Understanding how all the different components fit together really helped our design understanding of systems. And design for manufacturing, as he was talking about, the sourcing. Since COVID, it's been really hard to order electronic parts. And so figuring out, okay, how do we purchase those parts? How do we get a drone in less than 3 months? How are we able to source the different equipment and parts for this project? And assembly optimization, as you talked about with the parafoil, so many different parts. Are we able to maybe make that simpler? Are we able to have somebody else do it? How is that going to work?
So there's a lot of possible applications for this in missions aviation and outside. A lot of these organizations right now are only doing drops because they're so dangerous in life or death situations. So one of the biggest applications we see for it is in the delivery of critical medical supplies. Things where when you fly out there and drop it, it must get on the ground 100% of the time or somebody's going to die. Additionally, with the earthquakes we've seen in Syria, there's a really big application for distributed disaster relief. When roads are out, you can drop supplies in, but you can't drop supplies across a wide area. With this system, you can put 100 of these in the back of a cargo plane, drop them, and they'll fly to 100 different locations. So you can spread a large amount of supplies across a large area really easily. Additionally, there's some really good applications within search and rescue and in last mile logistics delivery. Rather than having a noisy drone fly into your backyard, a parachute system can come silently land in your backyard, and then you can just put a return label on it, stick it in the mail, and it'll go back to Amazon wherever you ship your package.
So what's next? What are we going to do with this? Is this done? Well, we hope not. We hope that we're going to redesign a couple of different elements of it and make it better and potentially make it a market-ready product. Woo! That's really exciting. So further testing is required for that, and understanding how do we make the drops more efficient so that it doesn't tangle around the rest of it. So it requires redesigning the physical shape of it and updating the flight vehicle hardware and defining the software and the flight planning capabilities, and also integrating some kind of visible interface between what the pilot or the user is using when they go ahead and drop it, and making that a little bit more user-friendly on the other side of that. So we would really sincerely like to thank the following people for their support of this project: Professor Wende, Professor Delp, Dr. Takahashi, for serving on our committee, and for Professor Wende, Mark O'Brien, and Kurt Patterson, who's sitting in the back row over there, for their support in acquiring the drone and being a part of the flight tests as well. And Dave Rask from MOF, Terry Harefield from JARS, and Matt Moed from Mission Quest for providing some of the background information while we were understanding more about mission aviation and more about the potential for Manna. So that concludes our presentation. We're going to open it up first to our committee for questions, and then we'll open up to all of the questions as well.
We can swap this around so that our community can talk.
Sound here.
Hey, is audio working?
Why don't you try to talk and we'll see maybe if we have audio.
I can hear everybody fine from here.
Perfect.
Perfect.
Okay, we have audio finally.
Yay.
Hey.
Any
Yeah,
questions
audio.
from our committee?
I don't have any questions because I've been asking them all along, but no, just awesome work. I've been impressed all the way. So good job. I wish I could be there in person.
Thanks.
But no, I don't have any questions. I think you did a good job in your presentation.
Can you hear me?
Yes.
Yep, we can hear you.
All right, good. So anyhow, I'm here in Tempe in my office. So one of the questions I have for you in this, I mean, I did see some circling, is what happens if you accidentally miss a waypoint?
Yeah.
When I've seen, some of the drone things flown by the evil Argue pilot for flying fixed wing, it does crazy stuff if it somehow, you have enough winds that it misses a waypoint. It tries to like circle back and it gets all lost. What did you do for that kind of stuff?
Yeah, so that's definitely a concern for the vehicle and how it operates. One of the best things we can do that is to launch the vehicle really high. That gives us the most flight time in the air. And then as soon as we get into the air, we're developing the capability to do wind estimation. And that basically lets us measure the weather conditions in that area and then adjust the flight plan so that we can fly upwind and we don't fly downwind away from where the landing zone is. From a practical planning perspective, every one of the waypoints.
But you could still mess up. That's what I'm asking. How did you do the
Yes.
failure? Okay.
Exactly, and there's a second layer to that as well. Even the military systems, when the military contracts these out, they give them with a percentage likelihood that they deliver. And for the military, that's around 85% of the time that package will arrive at the destination. From a practical standpoint, the flight control system and the global path planner monitor the altitude for the waypoints. And every waypoint, we pre-generate the flight path, but if we're dropping faster than we expected, so that we won't be able to make it to the destination, it automatically skips waypoints to shorten the flight path and get to the destination if the flight conditions are rapidly changing like that.
Understood. Good idea.
Thank you.
Hi, this is Deana Delp. Lukas, I want to geek out with you for a little bit on the control system. So I think in your thesis itself, you mentioned looking at another, I think it was another student's research that they had done to help develop this. Did you make any changes to what the prior student had done, or what changes did you make to the control system?
Yeah, so there's actually, I'm taking class right now with Dr. Sangram Redcar, who's a robotics professor here on the Polytechnic campus. And he had a PhD student, I believe, last year, who was working on paraglider dynamics and how to build a control system for them. So it lined up very closely with what we were doing. He just took a more theoretical look at things. From his standpoint and the way he designed the system, he worked a higher cost autopilot and a tool chain of systems that would have made the system automatically cost over $300. So he built a lot more complicated system that in some senses is more robust, but introduced a lot of cost and complications that we didn't really want to have at the beginning. So we built a much lighter weight system that, our entire electrical system is in the range of $80 rather than $300 for the autopilot. But with some recent advancements in some of these autopilot hardware packages, the price has now come down to in the range of $50 to $60. So for our next revision, we'll probably look at using some of these off-the-shelf systems that have better performance in the software than what we can write ourselves. Instead, just augment them rather than try to replace them completely.
All right, and that was something in your slide. I think you mentioned you don't have a wind estimation right now, but you want to continue work on that. Is that something you see yourself doing in the near future?
That's definitely one of the things on the controls end that we have to look into more. We did some simulation testing of it and it's promising. Basically, the idea is when the vehicle, if we tell it to fly in a constant radius circle, just turn at the same speed, in no wind conditions, it'll make a perfect circle. But if there's a wind going a certain direction, it'll actually end up making an oval path. And we can directly convert the shape of that oval path, how much it's squished from being a circle, to determine the direction and the magnitude of the wind at that point. So we have the theoretical, information in place to calculate that data. The problem is the flight time dropping from a drone is so short, we can't actually make a full turn before we hit the ground.
Yeah, I'm very impressed. I mean, you were showing this to us, when you were doing the simulation. So to go from a simulation to a prototype to actually testing and seeing, some good results is very impressive in such a short amount of time. So what you guys have done is just wonderful. I have just a couple more quick questions. So in the future, so when you see this as a more fully developed product, would it be something you could adjust the weight of the payload pretty easily for your system? So if you're, dropping something that's very heavy, maybe like some rice or things that are very dense versus things that aren't as heavy, would you be able to make that adjustment fairly easily?
Yes, we would. And the reason we can make that adjustment fairly easily is because we designed the parachute in-house. And so we can scale the parachute up in-house to be the size that we need it to in order to compensate for that.
Wonderful. And then my last comment is, have you guys heard of Venture Devils?
Yes.
Okay. So yes, they love it. You know, if you have something already partially developed, they're great at helping you kind of see that through on the business side. So good luck with this. But yeah, what you've done for your honors thesis is just wonderful. So I'm done with my questions.
Okay. Thank you so much.
Yeah, one interesting observation on the business end of things is MAF is one of the biggest organizations in this space. They operate 41 aircraft. So there isn't really a huge market right now to sell hundreds or millions of these units. It's not going to become the next iPhone. So from a business standpoint, it's really tricky to figure out what the best business model is to get this out there and sell it, especially because these organizations are nonprofits. So there's not an easy profit model from a business sense to make money off of it. So we've looked at maybe doing something where, for example, we sell one unit to a commercial client at a higher cost, perhaps $1,000 per unit, and that subsidizes the cost for a nonprofit client down to the $200 range. So we can balance that across basically working public-private partnership like that.
Right. Do we have any more questions from our committee before we open it up to everybody else?
And Dr. Takahashi, to answer your question, I think Professor Wende has the approval link, so he can coordinate with you guys on that.
Yeah, I'm just looking through all of my emails right now. Yes, doctor, if you don't have the email, I'll forward it to you for the approval.
Great. I think we can go ahead and open it up to questions from anybody else that here in the room or on Zoom. For people on Zoom, you can either ask a question in person or Noah's keeping an eye on the chat if you don't want to talk over somebody here in the classroom. But, yeah. Any questions?
Yes.
Just curious, I know you're talking about from the aircraft down to the ground. What is the thought on the actual retrieval? If we're dropping this into terms of lack of infrastructure, is this a one drop get it, or is it designed to be a reusable?
So it's designed to do both. So in a situation where we can't retrieve it from the people below, it's typically life or death. And so in that case, the $200 cost of the vehicle is negligible. And so it can be used for that, but in places with greater infrastructure, we're able to package that back, like he was talking about earlier, potentially slapping a label on it and bringing it back.
A lot of these organizations can, for example, hike into those locations, but it'll take somebody 3 days to walk in. So if they're bringing in a lot of things, they can potentially bring out these, or they can just take the guidance unit and leave the parachute. So there's choices about what parts they want to keep or get rid of.
Yeah.
Tested with the drone, pulling it up and then dropping it. And as you mentioned, it's a very quick drop, so you don't have a lot of time. When or how will you be able to test it from an actual airplane? And do you see a big difference between those two different tests?
Yes. So the speed at which the unit is dropped from the aircraft is going to be the next step for that, because we're dropping it now and it's still before it drops. So the next element is adding, we have a drogue parachute right in front, which would slow the parachute, this flight vehicle, down enough that it could built properly. But in the United States, it's really hard under the FAA regulations to test this from an actual aircraft because they see it as a hazard, which it is. So in order to do testing for that, it would be much easier for us to go to a different country in order to test this.
And from a safety standpoint too, we also want to do a lot more testing from the drone to ensure that, for example, we can inflate a really high percentage of the time. Right now, there's only a good inflation about 40% of the time, but that needs to get up to a higher 90, 95% before we're spending $100 or $200 an hour on an airplane to drop a vehicle that we can't reload really quickly. Exactly, so we're set. Any other questions?
Oh, we got a couple. Right.
How does it determine when you're clear?
Yes.
So that is something that we're looking into with the difference between GPS altimeter and barometric altimeter, being able to talk to each other and understand exactly how far away it is from the ground. So we can use a couple different sensors in order to sense directly beneath us and directly in front of us. So that is another capability that we'll have to test in the future.
And along with that, obviously, you know, the first you have things all the really big impact.
Mhm.
So the last foot kind of thing, you're probably going to try to do the wind. Are you planning on setting up to land into the wind and give it a gentle?
I think that's the hope at the moment. But that again will have to come with further wind calculation testing as well. Yeah. Saw a couple more hands. Yeah.
This full vehicle has dropped, this wing has dropped about 30 times, and this vehicle has dropped about 15 times. So this is the one that we dropped from that drone just a couple weeks ago. And it's still intact.
Yeah. Yep. Because the military is using the JPADS version, which is doing basically the same thing, just on a much larger scale.
Yeah.
That each unit is approximately $300,000 to manufacture. So.
What do you picture as your deployment method here? So you have a drone shoot, packaging, you get it safely out the door and deploy.
So with that, the human interface element is another part that we're going to have to go about. But I think the general idea right now is getting like a green light and saying, okay, this is the drop zone. And so once the person sees it, then they will be able to manually take it out of the aircraft. And so that is still a harder portion just because it requires a 2-man crew in order to be able to do that.
And then once it's released from the aircraft, similar to manned skydiving, or like a static line jump, you've ever seen the military does this a lot of times with their people. They release a drogue parachute and that decelerates the vehicle down to speed. And then this parachute will be folded in a bag and it gets released once the vehicle is at a speed that's safe for the wing to inflate. If we deploy this right off the bat, the vehicle experiences something like 20 G's of acceleration and it will shred. So we have to slow down first so that we can deploy it safely and it will actually inflate.
And it seems like by using a deployment bag, that may eliminate a lot of your inflation.
Exactly.
Yep. Yes.
You mentioned that you can distribute a number of these parachutes, and then does each of them need to be controlled by one person, or one person can control like 10 or 20?
Yeah, so once the system is released, it's fully autonomous. There's a light on top of it. When you get inside the drop zone, that light turns green. As soon as it detects the acceleration event of it coming out of the airplane, it knows it's in flight and it will handle everything itself. So it doesn't actually require a human to operate it in that sense. So you can deploy 20, 50, 100 of these at a time with a single person. It's just a question of how fast you can throw them out the cargo door of your airplane.
Yes. This current one is designed for a payload of approximately like 3 to 5 tons. Yeah.
Going back to the freeway, you mentioned that in certain applications that there would be some time for this module or this system. Curious with what's on board with it, the mechanics and changing the lithium battery, the possibility of it rupturing because of your environmental soil or water, or even setting fire to the
Yeah, the safety standpoint is really critical, especially the electrical system, because we don't want to cause a fire in flight or on landing. Some of the changes we can do to do that, right now we're using a standard RC airplane battery. It's really cheap and easy for us to get, and it's easy for us to use. There's some safer battery chemistries out there that are not prone to rupturing and catching on fire if they get damaged. Or we could even look at using single-use batteries, and we're like putting a whole bunch of AA batteries in this because it only needs to fly for a short period of time if it's then going to sit dormant for a couple months until it's retrieved. So depending on the application, there's some different options there.
Have you guys have any measure certain things, if either the user or the computer recognize that the population is like that we could be, or the parafoil of the device itself will be maintained or if
Yeah.
it recognizes that
Mhm.
it's
Yeah.
gonna crash, then they.
Yeah, so the one safety measure from a guidance perspective is that it looks for, as it sinks, it will try to get to the waypoint closest to the destination. So for example, if it's descending 3 times faster than it should be, rather than take a really long path to get to the destination, it will automatically cut to the shortest possible path to get to the destination. The idea is we want to get as close as we can. And this one also has wireless communication capabilities. So for example, you can have a device on the airplane or in the ground that receives a position from it as it's in flight. So if it crashes somewhere else, it can report back that position, or you'll have the last known position of it to go retrieve it.
And then any questions in the chat? No? Perfect.
You talked about, aspect where you've got backup from the system. Is it operable with only one of the 2 controlling arms working? Or any idea about that? I mean, I realize you probably didn't test it, but find out, but just from your design, you believe it would be at some control capability with just one system.
I think it could. It would be like operating multi-engine aircraft flying one engine though. So in operating and pulling the servo, it's like pulling a brake on one side. So really, we'd only have the capability to maneuver it and circle it in one direction. So ensuring that it doesn't move in that direction or continuing to move it would allow us to do as straight of a line as possible.
And as far as the impact, this is one that didn't exactly, have we considered some type of, I don't know, airbag, which would probably be complex, with structural cardboard or something using crash resistant systems?
Yeah, so one of the next design changes that we'd probably make is instead of using the Tetrix kit, we would likely 3D print something to house it instead. And so you can 3D print different kinds of materials. You can 3D print a harder brittle plastic or something closer to TPU. And that is a combination of plastic and rubber so that when it hits the ground, it's actually able to bounce and absorb some of that. So those are some of the design changes we definitely look into so that it's not taking in 100% of the impact and shattering the acrylic that we had in the front. Yeah. All right.
Thank you so much for coming, everyone.
Yeah, thank you for your time. Thank you for supporting us. This is fantastic. That's it. You're welcome to head out or chat either way, but thank you for coming.
Great job across the board, you two. Congrats.
Congratulations, great presentation.
Thank you.
Awesome job.